Okay, I did upload the slides for today. Okay, they are slightly modified from the slides of last semester, but you have them. But we're gonna have a challenge today, because today's class we're gonna be talking about statics, and statics is a lot of formulae. It's a lot of uh, math workout, and they're pretty hard to do in the slides. So I'm gonna try to do them in a notebook that I have in a kind of whiteboard in my tablet. But just be patient, bear with me, because it might not be as nice as if I did draw them in an actual whiteboard. So I won't be following exactly the slides, all right? Just loosely, because you can read the slides later on, and I don't think it's very interesting for you to hear me read what you can also read. Okay, so today we're going to be talking about statics. Uh, Statics, I think, is a pretty cool part of this course. Uh, it's uh, it's simple enough from a physical point of view, but it might be challenging from a computational point of view. Okay, might be. It's not super challenging, but I mean, if you guys are good structural designs, you're going to enjoy this part. Uh, so I think it's interesting. And today we're going to be talking about fluids at rest and how pressure distributes within the fluid. Okay, we're going to try to end with how to compute forces due to this fluid at rest onto surface, onto how you say, not curve, planar surface, flat surfaces. Uh, so hopefully it should be more or less straightforward, but we're gonna have to do some math, and for that I'm gonna be supporting myself with this notebook. Okay, so let me see how I do this. Okay. Before that, let me tell you, I uploaded the videos. I received a couple of questions, and I uploaded the videos again, but into YouTube, and you should be able to see the closed captions now. So if you can't, let me know, but it should be there. And there was other thing. Oh yeah. And just be aware that we're recording this class, and we're also recording the messages. So anything you say will be saved. So be wise with with what you write down. Okay. Um, so you should be able to see my notebook, right? Is it better if I put it landscape, or do you see it well enough? I'm gonna assume you can see it. Okay. So pressure, I mean, a fluid at rest. Normally, yeah, my question is, bear with me. If I do this, do you see it better? All right. Normally, let's say you want to do an structural design, or have you guys taken soil mechanics already? But when you want to do okay, so some of you know statics. You should, I think, for taking this course, and some of you have taken soil mechanics. So whenever you want to analyze the internal stresses on a body, typically you take let's say a differential slice of the body. So we're going to be working on a plane, right? Only on a only on 2 dimensions, just to convey the ideas, and then you can extend it to the third dimension, which is going to be depth. So for now, only think on lateral and vertical dimensions. So let's say you have a piece. Yeah. Let's say you have a piece of whatever. Okay. It's a bit challenging to draw with this, but bear with me. So normally you have a piece of solid or fluid in our case, or a building or whatever. You're interested in determining the internal forces, the internal stresses, which are going to be normal to this element, and also going to be tangential or sheared. So you're going to have, and this normally go like this, right? So let me, and this is going to be like a very small unit of fluid in our case. Okay, and we want to compute the distribution of these forces, okay, of these stresses. The important part here is that we're talking about fluid at rest, and fluid at rest, we know from the previous class, is that the shear stresses. Well, I want to draw this red. Shear stresses tau are going to be proportional to the deformation, to the derivative of the deformation, to the gradient of the deformation. And if we have a fluid at rest, that means, let's say we have a fluid. Here's the free surface. The free surface is the limit of the fluid, in this case to the water, to the atmosphere, is the top part of the water, or where the fluid ends, in the top part. So if we have a fluid at rest, then we have velocities which must be zero in all directions. Velocity in the lateral and in the vertical has to be zero. And if velocities are zero, the gradient is also zero. So if velocity here is zero, so let's say this is v1, this is zero, and this is v2, and it's also zero. I'm sorry, zero. Then the gradient here, dv or dy, is also zero, right? So this is zero. And if this is zero, then tau is zero, right? And if tau is zero, then the shear stresses within a fluid are zero. That means that all of these guys are zero. And they only remain the normal stresses. And what we normally call a normal stress is a pressure. So within a fluid at rest, the only internal stresses are pressure, which are these guys here. So this is pressure. So this is pressure, and this is some other pressure. Let's say Z1. This is pressure Z2, and this is pressure X2, pressure X1. This is assuming a coordinate system like this. Okay, I'm sorry for the for the school children level of the drawings, but it's the best I can do in these circumstances. Okay, so in a fluid at rest, we don't have shear stresses. We only have pressure. Okay. Now the question is, how does pressure distribute? How are these guys related to each other? Okay. And in order to answer that, we're going to be doing two stuff. Okay. The first one is called Pascal law, which is the one we're seeing here. So bear with me a bit. Let's say we have a wedge of fluid. A wedge is una cuña. It's nothing more than, let's say we have a coordinate system like so, and a wedge is something like a triangle. But keep in mind that there is another dimension in the depth, right? Like into the screen. Okay, and in this wedge, we're going to have different pressures. We're going to have one pressure here. We're going to call px. Now, let me draw this with another color. We're going to have px. Px acting in this direction. We're going to have pz or z. I don't know how you call it, but you know, zeta. And we're going to have here some p. Let me call this s. And let's say this is an arbitrary angle. Okay, and on top of that, this wedge, it has some weight. Okay, so if we do what we want to what we want to determine is how do these three pressures compare to each other. And for that, we need to look at the geometry of this wedge. Okay, so let's assume this wedge is small enough, like really small. So this difference, this part here, we're gonna call dx, could be delta x, and this part here and this part here is gonna be dz. Then this part here we're gonna call ds, right? But from geometry, we know that ds times sine theta is going to be dz, and ds times cosine theta is going to be dx, right? By trigonometry. Okay, we know that. And now the pressures acting into this wedge, infinitesimal small wedge, are going to be equal to the pressures times the area. Again, let's forget about the depth. So we're gonna express our forces like forces per meter of depth. We can assume this wedge is only 1 meter depth, and then you can extrapolate for the third dimension if you want. So if this is the case, let me go back to the black one, and we do the sum of forces in the lateral dimension and x should be equal to the pressure x times the area, which in this case is just delta z, minus the pressure s times ds. So that's the total force acting on the wedge, actually on the wedge. And this we should decompose it on the right direction. So we should decompose by sine theta. And since this guy is at rest, this should be 0, right? So, but then again, let me just scroll a bit. If you look at this, delta S is equal to delta Z is equal to delta S sin sinus theta. So we can remove these two, and we end up with Px being equal to Ps. So that's the first equation we have. And if we repeat this for the vertical dimension, so we do sum of all the forces in the vertical in Z, that would be, let me just scroll a bit. Okay, going up, we have Pz times the area, which is delta x. And going down, we have, so we're going to put a minus, we have Ps, Ps times delta S, and we have to decompose this for the right angle, which is going to be cosine theta minus the weight of the wedge. And the weight is nothing
Profe,
more. Yes.
there are forces, right? No, no, not pressures.
Yeah, good question. Because this is an important distinction. Px, let me just highlight this. Oh, come on. Px, Pz, and Ps, these are all pressures, okay? What we want to do is to determine the internal pressures of the fluid. But every pressure can create a force. So the force that Px, for instance, Px creates on this face is Px times dz, because the area is dz, yes, times 1 meter depth. Where these guys here are measured, if you want, in Newton per meter, because we're missing one dimension, right? In the slides, it shows the 3 dimensions, but I think it's easier just to look at it in a plane. So our aim is to determine how the pressures distribute, but in order to do that, what we're doing here is computing the forces that these pressures create, and this is key for all this chapter of hydrostatics. So it's a very good question. I hope I make it clear. If not, this is the time to keep digging.
It's clear enough to me. Thanks.
Excellent. Now I got another question. I'm sorry, I didn't read it. I recommend you. I'm reading my tablet. I don't know if you can see me. So probably I might miss what you write in the chat. So feel free to interrupt me and just throw your questions. I don't mind, because otherwise I might miss it. I'm being asked, delta Z is the area? No, and it's a very good question. And let me try to answer you now. So I realize this doesn't look very nice. Okay, so this wedge is a triangle that has some depth, right? So let's say the volume oh the volume of the triangle is going to be the x times the z half times 1 meter depth, right? So you can see this is volume, but it's expressed by area because we're only considering a plane here. But for all practical matters, you can assume this is 1 meter depth, that 1 meter into the screen or into the whiteboard. So that's actually the volume of this wedge. And why is important? Because the own weight of the wedge depends on the volume. So if we come back here to the sum of vertical forces, we said we have the force that Pz is creating upward over an area of delta x minus the force Ps over the area delta s, but projected by the cosine, minus the weight, which is also going down, and the weight is nothing more than gamma, which is the specific weight or the specific gravity, times the volume. And the volume is what we just said, is delta x delta z half, and this again should be 0. Okay, so if we look at this little guy here, the other geometric relationship, delta x is just delta s times cosine. So delta, let me use a more colorful one, delta x and delta s cosine and delta x all cancel out, and we end up with this equation, which is key. All right, and it says the Pz minus Ps is equal to gamma dz half. Okay, So the difference between the pressure at the bottom and the pressure at the bottom here and the pressure on this diagonal side here only depend on the let me highlight this with another one, only depend on this little guy, on the difference in the vertical, okay, times gamma. Okay, so if you take the limit of this, if you take the limit when delta z goes to 0, then the limit of this is that pz equals ps. So we have this equation and this equation. And what this is telling you, and this is very important, is that the pressure in a very small parcel of fluid, so small that you can consider it a point, the pressure in the vertical, in the lateral, or in any direction, because gamma is arbitrary here, the pressure in every direction is the same. Okay, so in a point, the pressure points to every direction. Okay, and this is key. It points up, down, lateral, in diagonal, and it's always the same direction. This is not the same for soil mechanics, for instance, but it is the case in fluid mechanics. So, and this is called, let me write this down. This is called Pascal law. Oh, I'm sorry, Pascal's law. It is on the slides. You can Google it, but it basically means that the pressure is the same in every direction. Okay, is that clear? Did I make it clear, or do you need another look at this? Okay, so Pascal law, pressure distributes in every direction, and it's always the same. Okay, as long as you're on a point. If you're on a point, pressure is the same in every direction. We'll get this later, but you can see that, and it's actually quite important. We'll see the details later, but you can see that the pressure in X, it tells you that it's the same pressure on S, but the pressure on the vertical, it actually changes with the weight. We'll see later on how that is, but it's interesting that the pressure in the horizontal doesn't really change. It's always constant, but in the vertical, it depends on the total area of your fluid. Okay, hopefully I will be able to save this and upload it to you as a PDF later on. So I apologize for how nasty it looks, but it's the best I can do now. Okay, any questions? No? Okay, so we know that in every point in a fluid at rest, we have no shear stresses and that the pressure is the same in every direction. That's what we know so far. Great. But how does the pressure change if you move to another point within the fluid? Okay. To answer that, I won't get into much detail. You all should be familiar with Taylor expansions, right? So it is in the slide, and you can have a look. But basically, a Taylor's expansion tells you that the value of a function in a point, given that you know the value of the function in another point, is equal to the value in the previous point plus the derivative times the difference between them, right? So, well, I'm actually going to write. Again, so let's say this is a typical example. I'm sorry if you've seen it, but I think it could be important. So let's say this is x, and this is f of x. Now, I'm sorry, and we're going to have some arbitrary function, okay? And let's say we know a point x0, so we know the point of f at x0. And we also know all the derivatives at this point. You know that the first derivative is kind of the slope and so on. And we want to know x at x1, right? So we want to know this little guy. Okay, Taylor tells us that f at x1, it's going to be f at x0 times an infinite sum of factors, right? So I'm going to write them down here, times the first derivative of f at x0 times the difference x1 minus x0. Yeah, and divided by 1 factorial plus, I'm sorry, minus f to the second derivative of x times x1 minus x0 square divided by 2 factorial plus, it goes on and on infinitely, right? Okay, so we're gonna use this, and we're gonna do a first order approximation, which means you only keep the first derivative, and it makes sense as long as your distance is small, right? If delta x, this is delta x, right? x1 minus x0. If that's small, then the first order approximation is sufficiently good, is sufficiently accurate, so you can use it. Okay, why am I bothering you with this? In the slides, you should be able to find this scheme. Okay. So I won't work directly on this one, but I'm gonna again write. Let me just grab this up. Again, I'm gonna write a new one, but only in a plane. Okay, we're gonna forget about a bit the depth. We're gonna stick only to an area, and then the same is going to apply to this direction perpendicular to the screen. So again, let's assume we have an infinitesimal small parcel of fluid, okay, and that we know the pressure at the center of the fluid. We know P, okay, and we want to estimate, and we know that P is pointing in every direction with the same magnitude, and we want to estimate P at the boundaries of this infinitesimally small volume. Okay, so the value here, I'm going to just write it down. The value here is going to be, we're going to call this, let me just look at my notes. I'm not improvising, not as much here. So the value here is going to be, and again, let's assume we have this reference, right? So the value here is going to be P. Oh, it's going to be P minus the derivative of P with respect to the vertical. So that's dP to dz times the distance between this point and this distance. Okay, and let's assume this volume has dimensions. I'm going to write this down here. This is delta x, delta z, and this is delta x, this distance, right? And this is delta z. Okay. So again, the pressure at this point is P minus the derivative of P with respect to z times delta z half. That's the pressure. And the pressure on top is going to be P plus dP at dz times delta z half. Okay, it's easy to see how this is going to be on the horizontal, I hope. So the pressure here is going to be, this is the distance delta x half, so it's going to be P times dP at dx times delta x half, and the pressure here is going to be P minus dP at to dx times delta x half. Are we all on the same page? Okay, these are the values of pressure, mind you. They are not forces yet. These are pressures. And these are pressures that are acting over these very small areas. What other force is acting here? Is the on weight of this small, really small volume. So we have the weight here, right? Acting on the center. So let's do again what we just did.
Profe,
Yes.
no caché bien el término de dp en dx y en dz.
Okay. You can ask, always you can ask questions in Spanish, but I'm gonna try to answer you in English just to keep it formal.
Okay.
But
No problem.
yeah, and but if we get stuck, I mean, I can switch back to Spanish a bit. Okay, so let me just take a detour here, and this is kind of a parenthesis. Okay, so dP at dz, this is nothing more than P prima, if you want. Is the derivative of P with respect to Z. The thing is that we need to be explicit with respect to which variables we're taking the derivative. So this is actually, I don't know if you can see this color, maybe. So this is the derivative of P with respect to Z. Is how P changes with respect to Z, or the vertical coordinate. And it's not explicit here, but this derivative, it's evaluated at this point, because we are assuming that in the center of our volume, we know everything. We know the pressure, we know the derivatives, we know everything. So P and dP at dz, dP to dz, are evaluated at the center of the volume. Okay, so this is all of these four expressions I wrote down are the first order estimation or estimate of the pressure at the boundary of this volume. This is a key point for the derivation, but it's also very important later on for how we compute forces. So it is very important that we're all on the same page. So the pressure, again, the pressure here, for instance, is the pressure here plus the derivative of the pressure with respect to x times the delta x that separates these two points, which is delta x half. Okay. Hopefully that makes sense.
And the second term is like the internal pressure of the fluid in this square, or in this half of square.
Yeah, P is the pressure at the center point. Yeah, that's P. What do you mean the second term?
The term that is after the sign plus.
dP at dz.
Yes.
Yeah.
And these are multiplied by the x half.
Yeah. Let me see if I can Okay, so this, all of these, let me just highlight. Oh, Sorry, I have a new stylus and I don't know how to use it yet. So let's stick with this function, with this expression a bit, okay? It is important, so let's take a few minutes on this. So what this is trying to estimate, we're gonna call this P. Wait a second. Maybe this will make it clear. Okay, so we're gonna call this coordinate x0. You have to project it here. I don't want to do it because I'll just I'll just do it. Okay, so this is P0 and this is Z0. Okay, so normally when we engineers we tend to abuse notation. So what we know is we know P at x0 z0. That's what we know. And we also know all the derivatives. We know the P at the x at x0 z0, and we know the P at the z at x0 z0. All right, we know this. What we want to know, so I'm going to put this in another, we want to know the pressure. Wait, I think it looks better. We want to know the pressure at, for instance, x0 z0 plus delta z half. This point is this point here. So we want to estimate P, the pressure, at x0, comma, z0 times delta z half. So this coordinate and this coordinate. We want to know that. And how do we approximate this? Well, this guy is going to be just P at x0 z0. So it's the pressure at the center plus a term which is going to be the derivative of P with respect to z, also at x0 z0. So you see this has units of pressure per unit length. So in order to make it a pressure, we need to multiply it by a unit length, and in this case is the actual length that separates the 2 points. So delta z half. This is actually it's not equal. It's an approximation, and it's a first order approximation. This is a Taylor series. This is a Taylor expansion. So if we know the pressure at the center, we are approximating the pressure at the 4 sides with these 4 relationships. Okay, these are our approximations. Is that clear, or do I need to?
Yes, it's clear now. But it's just the pressure in one point, right?
Yeah. So basically, we're getting the pressure in these 4 points, in this point, in this point,
yes,
this point, and this point. And we are assuming later on, we will assume that they act on the full area, which makes sense if this is a really small element, right? Because yeah, here it is explicit where we're evaluating everything. Here is just implicit that we know all the values at the center. Okay, good question. Let's move on. Let me see. Okay, so now we do what we did before, which is how's it called? We're going to sum the forces on the horizontal. So we're going to sum the forces in X, which are going to be, we're going to assume that the forces are equal to the pressure times the area they are acting. All right. So hopefully I will be able to put these equations in this notepad. So going to the right, we have this force here, which is going to be equal to the pressure there, which is P minus dP at the x times delta x half times the area in which it is acting. Yeah, we're gonna have a break in 10 minutes. So bear with me this 10 minutes and then, oh, we already been an hour going on. Okay. Yeah, I'm sorry. Let's have the break now. So I have 17:38. See you guys in 10 minutes. I'm sorry, I didn't read that. Okay, see you in 10 minutes. Okay, sorry about that. I just put an alarm to mark these recesses, so we should have two of them in the if we are for the full 3 hours. So next Monday you're gonna hear the alarms ringing. Okay. Hopefully everyone's back. There. Hopefully everyone's back. Um, okay, so we left off saying that if we have a very small volume and we know the pressure and the derivatives at the center of this volume, we can estimate the pressures at the boundaries. All right. And now, if we know the pressures, we can do a balance of forces, right? So if we do this balance in the horizontal, in the x direction, we get a positive value, which is the same as the pressure in the left side surface times the area of that surface. And we're doing this all by meter of depth. So we only need to multiply this by delta z, right? And in the opposite direction, we're going to have a negative force, which is going to be equal to the pressure on the other side, which is P times dP at dx times delta x half multiplied by the area of that side, which is again delta z. And this should be 0 since we are in equilibrium. Okay. So from this is straightforward. Then the delta z cancel out, right? So let's write down what's in the parentheses. Okay, so we get from this one we get P. I'm gonna just write it down all dP at dx times delta x half minus P minus dP at dx times delta x half again, and this is 0. And here it's clear that we can cancel out the pressure, and we can also cancel out dP dx. So what we get here, this is the result, is that dP at dx, it's 0. It's 0. So the gradient of pressure with respect to the horizontal direction is 0. What does that mean? Is that the pressure doesn't change if you move in the horizontal. Okay, this is a very powerful idea, meaning that if you have 2 points at the same vertical position, then those 2 points will have the same pressure in a fluid at rest, in a hydrostatic condition. Okay, so this is one conclusion.
Excuse me,
Yes.
could you repeat that?
I'm sorry. Yes. What I'm saying is that if the gradient is 0, the horizontal gradient is 0, that means that 2 points that have the same vertical position will have the same pressure. So let's say you have a fluid at rest, a pool, for instance. If you measure the pressure at 1 meter depth, 1 meter below the surface, on one side of the pool, and you measure it in the other side 1 meter below the surface, you should measure the same pressure because they are at the same vertical position. So the gradient in the horizontal, if you move from one side to another, there should be a gradient in the horizontal, and in a hydrostatic position, the gradient is 0. The gradient in pressure is 0. So the horizontal gradient in pressure is 0. We'll get to that later on, but this is one of the first conclusions. And the other one is in the vertical distribution. Okay, so let me do the same, but for the vertical forces. So we have the sum, oh, sorry. The sum of all the vertical forces are going to be the following. Okay, so going up, we have the pressure at the bottom of our element. So that's going to be P, P times, I'm sorry, minus dP at dz times delta z half. So that's a pressure acting on a surface of delta x, all right? And going down, we're going to have the pressure at the top, so minus P plus dP at dz times delta z half acting on an area delta x. And we're also going to have the weight. So I'm going to put it in below, but it should be on the same line, right? So I'm going to put it here, minus the weight. And the weight is nothing more than gamma times the volume. And the volume of this thing is delta x, delta z times 1 meter depth, right, that we're considering. And this should be 0 because this is in equilibrium, okay? Then again, it's pretty easy to realize that we can cancel out the delta x's. I'm not gonna write the full thing again because you can see it's analogous, but we're also gonna cancel out the pressures, and we're gonna end up with the following. So we're gonna end up with let me see. So we're gonna end up with minus delta p at dP at dz times delta z minus gamma delta z. This should be 0. Again, we can cancel the delta z, and this is the main result, and it's very, very important. So we get that the P. I don't like this. Let me just put it a bit more thicker. Okay. So we get to the P at dz is equals to minus gamma. Okay, and this is a key finding. So what this is saying is that the pressure changes in the vertical proportional to the weight of the fluid. So the only thing that's driving the increase, also, yeah, look at the minus. So this is telling you that the pressure is decreasing upwards, meaning that it is increasing downwards. So if you go down, your pressure is higher. And how much higher? Well, it only depends on gamma, which is a measure of the weight of the water. So if you're 1 meter below the surface, the pressure is equal to that meter of water, of the weight of that meter of water. Okay? So this is the hydrostatic law. So we have the Pascal law that says that pressure is the same in every direction. And we have this hydrostatic law that says that pressure only changes in the vertical, and it changes proportional to the weight of the fluid. It's not necessary for it to be water, it can be any fluid. And these are really key ideas. You can show, but I'm not gonna do it, but you can show that dP at dx, you can easily show that dP at dy, it's also 0. So in any horizontal direction, the pressure doesn't change, only changes in the vertical. Okay, and these are the hydrostatic law. Now, what does it mean? What's the implication of this? Let me see if I'm gonna keep on this. So let me write a new section or something. So what's the implication of this? let's say we have this equation. We have, I'm struggling here with my tablet. Okay, let's say we have dp at dz. We know this is minus gamma. So this is a differential equation, right? So we could integrate it. So we could integrate this, and we could say this is a partial derivative, but we could express it as a total derivative if it's the only relevant direction. So we could say, okay, dp is equal to minus gamma dz, and if we integrate this, we can get to this equation. Okay. So let's say we have, whoa, my pencils just reset it. Give me a second. Let's say we have a fluid at rest. It has to be at rest for this thing to be valid. So this is the bottom. And let's say we have a couple of points. Okay, we're going to call this 1 and this 2. Okay, and let's say we know we have an instrument measuring here at 1. So we know P there, and we know everything that we need to know there. And we want to compute the pressure at 2. Okay, so how could we do this? Okay, we integrate this equation, and we integrate it between the pressure at 1. We're gonna call it P1. The pressure at 2, we're gonna call it P2, and Z, we're gonna integrate between Z1 and Z2. Okay. If you remember, if this is water, then gamma really doesn't change with depth, right? Because it doesn't change with pressure. So we could move gamma outside of the integral. So if we do integrate here, we would end up with P2 minus P1 is going to be equal to minus gamma Z2 minus Z1. Okay, and we can call this delta Z as long as it is positive, right? So what this is telling us is that I'm gonna rearrange this, but this is telling us is that P2 is equal to P at 1 minus gamma delta Z, or it's the same, P at 1 P at 1 is P2 plus gamma delta Z. Okay, so if we take the lower equation, this is telling us that the pressure here is going to be the same pressure here times the weight of the water above it. Okay, which is just gamma times the difference in height. This is delta Z. Of course, this is missing 2 dimensions, right? Because gamma times delta Z has dimensions of has units of pressure and not force, and the weight is a force. So this is just how the pressure changes. Okay. And from here it comes the idea of pressure expressed as meters of water. Have you ever heard that? I think I said that in the last class. You know, an atmosphere is more or less equal to 10 meters of water, meaning that if you go below the surface 10 meters, you're gonna have the same pressure that you have at an atmospheric pressure. So 10 meters of water weigh exactly the same as, I don't know how many kilometers of atmosphere we have, because water, of course, is a lot heavier than air. I'm not gonna do it here, but I'm gonna let you. I'm gonna let you the question. So what if gamma is not constant? For instance, in air, for instance, in the atmosphere. So in that case, you have your integral of dp, and then you have your integral of gamma, which might be a function of z, dz, right? So gamma, or actually rho, the density, might be changing with the depth, right? Which is the case on air. You can look it on yourself, but you end up with an exponential distribution. I won't do it because it's not relevant for us. But keep in mind that when you see these kind of equations, it is assuming that gamma is constant, and that means that gamma doesn't change with pressure, and that means an incompressible fluid. This is only valid for an incompressible fluid at rest. Okay. The atmosphere is never at rest also, so that's another complication. Okay, so the important thing here is that between these 2 points, let me just draw it here, between these 2 points, what we have is a linear distribution, and this is really important. So here we have I'm going to draw this to this side. So here we have this pressure, and here we have this other pressure. Okay, so this is P2 and this is P1, and these two change linearly. Okay, this is not very straight, but you get the idea. Okay, and actually this change linearly all the way to the top, where the pressure here it's 0. Okay, it is 0 with respect to the atmosphere. You will see it on the slides, but you know that on the surface of the water there is an atmospheric pressure, but here we're normally interested in the relative increase on pressure, not in the absolute pressure. So normally we're going to call here a P0 or P0 or or P atmosphere at the value of the pressure of the atmospheric pressure, and from that point on we have a linear increase as we go down into the fluid. Okay, when you measure, for instance, the air on your bikes, and you inflate them at, I don't know, 40 PCIs, those are I don't know exactly the unit, but whatever it is 40 PCI above the atmospheric pressure. All right, it's pressure square inch. I'm not sure. So when you go 1 meter down the water, you have 1 meter extra of water on top of the atmospheric pressure, or on top of the 10 meters of water that are equivalent to the atmosphere. Okay, normally we will talk about relative pressures unless it is stated otherwise, and normally when we compute forces, we'll also compute the forces relative to the surface. Okay, so keep that in mind. It's not very important. Okay, so yeah, I won't go into much detail on this. You can read. I think the important part here is the derivation, but there is one point that I want to make again. I already did it. I already said it, but I'm going to say it again. And it is the following. Let's say you have a pool, okay, and this pool has some kind of island in between, and there is just a tube that connects these two. Okay, so this is concrete or cement or whatever. And this part here is some kind of island in the middle. This is looking for the side, okay? And this is your water level. And these two sides are connected. And this is some fancy bar at the center of the pool or whatever. It doesn't really matter. Okay, and let's say you have the pressure here at a depth of h, whatever h is. If you measure the pressure here at the same h, so these two are at the same depth, and the water between them is connected, then we know that the P at the X is 0. So the change in pressure along this red line is going to be 0. So all along this red line, you have the same pressure. Here you don't have pressure in this solid. So, but in the water, all along this line, you have the same pressure. And that pressure is just gamma times h, okay? And if you want, plus the atmospheric pressure, okay? It's not pretty relevant, but you know, it's optional. So I'm gonna say it again. The pressure only changes with the vertical. The deeper you go, the higher the pressure. It doesn't matter the shape of the container. It doesn't matter all the variations to the side are null. The pressure doesn't change when you move to the side. It only increases when you go downwards. Okay? Is that clear? Did I make myself clear, or are there any doubts? Okay, people are leaving, so I'm guessing I'm very boring right now. But okay, that's the thing we're doing now. Okay, and here you can see in the slides there are some values of the atmospheric pressure. Again, one atmosphere is more or less 1 bar. It's a bit more, but 1 bar is more or less 10 meters of water. In Spanish, we call it metros columna de agua. It's a bit more, but you know, that's an order of magnitude. And you can also express this as millimeters of mercury. You've seen it, right? And I want to show you how it works, because it's actually pretty interesting. So let's say, let me just separate this. Okay, let's say we have a container. So it's a solid container, and we have mercury in it. Okay, mercury is this metal that the thermometers are made of. And in order for this to work, we need a long tube of, normally is glass, containing the mercury. So I'm going to try to draw the mercury. So let's say the mercury is going to be up until here, and here it has to be open to the atmosphere. Okay. Okay, the color is not a very nice option because it's similar to the black one, but all of this has mercury. Okay, and it goes up the tube up until this value. Okay, there's probably an option to fill this out, but yeah, I haven't found it, so we're gonna have to do with the hash. Okay, and this, let's say this is a certain height. We're just gonna call it h. Okay. What's going to happen here is that we're going to have the atmospheric pressure acting on the free surface of the mercury. So here we're going to have atmospheric pressure. I'm sorry to write in red, I think I shouldn't, but it kind of contrasts. Okay, so if we do an analysis of this point, here, this line, we said if this fluid is at rest, all along this line it has the same pressure, right? So on each side of the this is actually a barometer. On each side of the barometer we have atmospheric pressure, and at this point, what's the pressure we have? Here we can assume we have vacuum. So here we have vacuum, or no pressure at all. So here the pressure here, let me just switch back to red because I like it. So the pressure here is going to be the pressure here with which is 0 because there's a vacuum, times gamma of mercury. We're going to call mercury Hg, which is the initials of the element, times H. Okay, so, and here we have atmospheric pressure. So these two have to be equal. So the pressure at the atmosphere has to be equal to gamma Hg times H. Okay, in a typical atmosphere, H is 760 millimeters of mercury. Okay, and this is one way that in the Industrial Revolution or a few hundred years ago we had to measure pressure, okay, using the hydrostatic principle. Okay, is that clear? In principle, you can do this with any fluid you want, but why do you think we do this with mercury and not water, for instance? If we did this with water, how high would be H? Okay.
10 meters.
10 meters, thank you. So if this was water, then H would be 10 meters. So we would need like a building to measure the pressure, right? So we use, or people used to use mercury because mercury is very, very heavy. I don't know if you've seen it. You can Google it, but you can have a, how's it called? Oh, I forget the name, but you can have very heavy steel elements floating on mercury for how heavy it is. A vial. I forget the name, but this thing that you can use in a forge, you know, to make a sword or stuff like that. Un yunque. You can throw. I don't know the name. I can't recall the name in English, but you can throw a yunque into mercury and it will float. You can Google it. It's pretty cool. So mercury is pretty heavy. So big variations in pressure mean it will only move slightly within the tube. You can also imagine that we use mercury to measure temperature variations. So density also changes with temperature. So you need to calibrate that, right? But I won't go into that now. Okay, another thing we can do is a manometer, and with this we're getting almost to the end of this part. A manometer is nothing more than a way to measure pressure differences. Okay, so let me just throw this. So let's say we have a pipe. Okay, we have a pipe and we have water flowing in this pipe. Okay, and we install a manometer. A manometer is is a small tube that we can put a valve here, and a manometer will come out here and then go up. Okay, and we get the fluid that is flowing in here. There is a fluid flowing in that direction, and that fluid will get into the valve right here and will fill this manometer up at a certain height. So all of this will be filled with fluid. It could be water, it could be anything. Okay, so the pressure of the fluid inside the manometer will be proportional to this height. Again, to the pressure will be gamma times height times h. Assuming a few things, like we know that here the inside the tube the water is flowing, but inside the manometer, this instrument is called a manometer, the water is static. So if it is static and the pressure here is atmospheric pressure, the pressure here must be gamma times h. So if we move laterally, we know we must keep the same pressure. So the pressure here is also gamma times h. And the pressure here must be the same pressure at the inside of the valve. Otherwise, there could be water flowing. You know, if you have a difference in pressure, water will flow where there is a smaller pressure. Although keep in mind that this is a relative difference in pressure. Okay, so this is a measure of this is a way of measuring differences in pressure. Okay, there are a couple of examples in the slides. I think they're pretty straightforward regarding this same idea of manometers. So I won't go over them now because I think the concepts of forces over surface are more important, and I think they are easy enough for you to work them out. Maybe in the recitation of this Thursday, we can look a couple of examples of manometers. But for now, let's just switch to forces over surfaces. So my alarm hasn't gone off yet, but I think this is a good moment to take a break. So I have 6:20. So see you in 10 minutes, please. Thanks. Okay, I'm sorry I took a few more minutes and I had to attend something. Okay, let's move on. I want to thank all the people that are still here. I realize it's late on a Monday, so thank you. Before we go on, let me. Oh, why do I have this? Let me remind you that this Friday we're gonna have the second quiz. Okay, so for next class we should be finishing the unit 2. So for next Monday you should read all the chapter 2, which is uploaded in Canvas. Okay, so we're gonna cover what we're talking about now and what we're gonna cover in next class. Okay, so okay, for some reason I have this. Okay, so be aware that this Friday, yeah, just like the last quiz is gonna be open since Friday, but you're gonna have time to turn it in and up until just after the class, like 1 hour after the class. I don't recall exactly how it went the first. The idea of that is that I could do it before the class, but really my goal is that you understand what we're talking about here. So you might not read the book. That's up to you. And you might be able to answer the quiz only coming to class. That's also up to you. But I guess if you really want to learn, you really have to read the book and then come to class and ideally ask questions and try to understand what's being said. Everyone can solve the quiz, but the idea is that you are able to later on apply this stuff. But anyway, so be aware of that. I will let you know in time, but I'd rather tell you that now that at the end of the class. Okay, if you follow the slides, there is a formal derivation of how to compute forces on a flat surface. I'm going to start backward because all the derivation we've done so far assumes that you know what a pressure is and how it creates forces. And you should, because you're engineers and you've taken physics already and you know calculus, so you should. So let me start from the end. Okay, let's assume again we have a pool. It bugs me that this thing resets my pencils, but okay. Again, let's assume we have a pool. So like this. Okay, so this is solid. And we have water on it. Oh, not very horizontal. Let me just, okay. And we're gonna have, this is pretty standard, we're gonna have a depth of h meters. Okay, and this is also gonna be very, very standard. We're gonna say that this pool has a width w. Okay, given that and what we just saw, what is the total force that the pool has to withstand at the bottom? So there is a force here. There is a force here applied to the bottom of the pool. You should be able to compute that, right? Okay, I'm gonna assume you guys and girls are following along, but the force is gonna be force. This is straightforward. The force is gonna be the pressure at the bottom times the area. Okay, again, we can assume that this pool has 1 meter into the whiteboard or into the screen. Okay, and the pressure at the bottom is going to be, anyone can write it down or tell me?
But sir, isn't easier just to calculate the volume and multiply that with gravity?
Yeah, I'm gonna get there.
Okay.
Okay, what you say, okay, let's say you have no idea of pressures, you know nothing about it, you just connected to the class now, so you don't know about hydrostatic pressure or anything like that. You say, okay, well, this is nothing more than the weight of the water, right? And the weight of the water, okay, I already used W, but okay, the weight of water, I'm sorry to repeat, is going to be the volume of this, which is H times W times 1 meter of into the screen again, times gamma, right? That's the weight of the water, right? And that's the total force that is acting on the bottom, right? But the other approach that I'm proposing here is, okay, the force here at the bottom is going to be equal to the pressure at the bottom times the area, okay? And the pressure at the bottom is going to be gamma H, and the area is going to be omega W times 1 meter into the screen. So you see, we get to the same thing, gamma H W, and here it was also, well, it's not in the same order, but it's the same value. So you get a sense that, okay, the forces created by pressure are pretty much related to the weight of the fluid, right? So there is no magic here. I'm going to tell you up front, my worry, I can show you the equations to compute forces on surfaces, but my worry is that you might try to remember the equations, but then forget how they are computed, okay? And if you know how to compute them, I mean, how to derive the computations, you're always going to be able to compute them, regardless if you remember the equations or not. Okay, so the force on the bottom is really easy. You could have done it just by the weight of the water. But what about the force on the walls? Okay, so there, I'm going to call this force Z. And there's also going to be a force on X. I'm sorry. So what's going to be the force to the wall? Okay, that's a bit trickier, but not too much. So first we need to recognize how pressure varies with depth. So here pressure is 0, and here pressure, we already said, here pressure it's gamma H, right? And it varies linearly, right? So pressure varies linearly. So you can see in the first part here, you have very small pressure, and here you have a very large pressure acting on the wall. Okay, so and here is where integrating will become handy. So you can think, you have to, I would recommend you to always think in differential terms. So if you think in differential terms, you can say, okay, let's take a slice here. It's not very nice. Let's take a slice. It's going to have a D. Sorry. Let me put this here. D set. How do you say? A width. Okay, a height of D set. Okay. So the delta force applied on this small parcel of the wall, that delta force, is going to be the pressure at that position times the delta area. And the pressure at that position is going to be nothing more than gamma times Z. We're gonna be measuring Z downwards, and delta area is going to be nothing more than the delta z. Okay, this is assuming that z goes in this direction. Okay, if it's in the other direction, then you're going to have a minus here because z is going to be negative. Is that clear or is confusing? Okay. And if that's the case, then the total force, then Fx is going to be nothing more than the integral of dF from 0 to h, assuming z again is not so clear. Okay. Okay, great. Let me just go back a bit. Okay, let me just draw it again so I can make it clear. Let's say we have a wall and we have water here. And we know that the pressures distribute linearly. Okay? So if we take a really small layer of width dz, and we're measuring z as the distance from the free surface, so this is going to be z. Here in this very small layer, we're going to have a delta force applying. You can see that the delta force here is going to be small and the delta force near the bottom is going to be larger. So the total force is going to be the sum of every small contribution. Okay. And let me just write down P, the pressure. Sorry, let me try to make this nicer. So P is going to be gamma times Z. So the deeper you are, the higher the pressure. And therefore, dF is going to be your pressure times your area, which is going to be gamma times Z times dZ. Okay, so if you integrate this, if you integrate your dF, you're going to be integrating gamma Z times dZ. Okay, and this is, so the total force is going to be gamma c squared half, right? Evaluated at 0 and at h. So this is nothing more than gamma h squared half, right? Everyone can follow that. So the total force on a wall is going to be this equation. Now you could memorize this equation and the equation for an inclined wall, or for, you know, I don't know, a circle and a sphere or whatever. But the important part here is that you understand what we're doing. Okay, so we are integrating over different depths, and at each depth we know the pressure, because the pressure only depends on the vertical distance to the free surface. Okay, and actually you can express this, I'm going to show you later, but you can express this as the pressure at the center of gravity of the wall times the area of the wall. The pressure at the center of gravity is nothing more than gamma times h half, and the area is h times the direction going down, going into the screen. Okay, which is exactly the same as this thing. Okay. Now you could remember this, which I'm gonna just show you in a moment. But this is to show you that you can always compute the total force by integrating the forces, the individual forces at each depth, which is the same that we did before. I mean, if you know the pressure at the bottom is flat, we know that the pressure is the same everywhere. So basically you're integrating the pressure over a delta area, you're integrating the area. So you get P times area, because you're integrating the area, okay? And here we're integrating along the vertical, so we know that the pressure is changing along the vertical, and we are, and the area is the same because it's a delta Z, so we're integrating how it changed. And since it is a linear change, the result is this parabola h square, okay? There is another.
Sir,
yes.
How would we? I have a bad English to start, but how do you calculate, for example, the pressure if the edge of the pool is cornered or like inclinated?
Okay, let's go by one by one. Let's assume this is what I showed you here is a particular example. Okay, I'm gonna show you like the general one, and we should arrive to the same result. Okay, so the general one is this figure here. The general one is here the orange thing is the fluid, and we have an inclined wall. Okay, and we want to compute the force in this portion of the wall here. Okay, so I'm going to show you step by step, and we should get to the same, hopefully. So let's assume now that we have you can go into the slides. You can go to this image. It's in the slide 25, so you can have it at hand. Okay. Okay. So this is the general case. So let's say we have an inclined plane. Okay. We have a free surface here, and we want to compute the force of the water over this plane here. Well, what you should keep in mind is that I'm going to draw it again, but the pressure distribution, if this is the pressure, here is 0, and here is proportional to the depth. So it's a linear distribution of pressures. Okay. I'm sorry for the mess, but this is pressure. So at every point in your surface, you're going to have a different pressure. Okay. So the vertical distance we're going to call h, and we're going to have a coordinate along the surface that we're going to have y. Okay, and what we're going to do is the same that we did before. We're going to take a very small slice of width dy, and we're going to compute the very small force that acts here, df. Okay, we're going to call the resultant force F. I think in the slides is Fr. It doesn't. Yeah, we're going to use Fr. So it's the resultant force. Okay. And again, we're going to do the same. So Fr is going to be nothing more than the integral of df. Oh, I'm sorry for the mess, but you get it. And df is going to be the same as the pressure at y times the area, which is the area. We're going to just write down. Okay, and if we have a position y, then h, and let's say this angle here is theta. So h should be y times sine theta. Therefore, the pressure at one point y would be gamma times h. So let me write that here. It's going to be the integral of gamma times the height, which is going to be, I'm going to write h, dA, and we know h is just y sine theta dA. Okay, and so this is the resultant force, and dA is the generic differential for the area. In this case, it's only the y, but you know, the general case is just dA. Okay. Now we know that, and this integral is over the area. Okay, in this case, if we start here, we're integrating over each small piece of area until we get to the bottom. So we're integrating from here to here. Okay. Now gamma and sine of theta, they are constant, so you can throw them out. So your resultant force is going to be gamma sine theta, and then you have your integral of y dA over A. If you remember, the integral of a coordinate over the area is a measure of a weighted average. Okay, so you know, the definition of a centroid is if you have an area and you multiply by the centroid, this is just the same as integrating the coordinate over the area, right? So your centroid position is nothing more than this integral over the area divided by the total area. This is an average, this is a weighted average. Okay, this is the definition of centroid that you must have seen on statics. So this is just a weighted average. Now we can use this because this integral might be tricky to compute because the delta area might be, you know, the surface you're computing might change. We normally draw it like a potato, right? It could be any shape. But this integral is nothing more than the area times the centroid position. So what we get from here is that the total force is gamma times sine of theta of the centroid position times alpha. And this part here is nothing more that you can replace this for gamma h of the centroid times A, and gamma h of the centroid is nothing more than the pressure at the centroid times A. Now the centroid is the point where you could balance the surface if you were to, you know, put your finger under the centroid, then the area wouldn't tip over, right? So if you take a square, the centroid is just the center of the square. But if you take a triangle and a rectangular triangle, then the centroid is 1/3 near the base, right? So, and if you look what we just did before, I told you this is the pressure. If we look at the wall from the water, the wall has a depth h and a certain width, whatever it is, b. So h half It's just a half of the wall, and it's the centroid of the wall. So if you compute the pressure at the centroid of the wall and then multiply that pressure over the area of the wall, you get the total force. And why is this? Because, like we said in the beginning, the total force is the integral of each contribution at each depth. And since pressure changes linearly, this is equivalent to compute the pressure at the centroid and then apply it to the whole area. You can think the pressure here, let me draw, if we draw the pressure distribution, is like that. So the pressure here at half point is the average pressure over the wall. If we cut this off, if we cut this, you could see that this triangle just fits here. So the pressure at the centroid, in this case of the wall, is a measure of the average pressure. And the average pressure acting on the whole area gives you the full force. Is that clear, or is confusing? I can tell you that when I studied this was confusing for me, but you know, some people are more structurals, and some people are more, you know, more engineers, so they can enjoy this kind of things. For me, it's kind of hard, so I'm trying to make it as clear as I can, and I think in the slides it might be a bit obscure. Okay, so the total force. Okay, nice to hear that if you study, you will get it better. I also think you need to read the book, you need to come to class, and you need to give it a thought. And I would highly recommend you to try to compute it on your own. Okay, I could just tell you, okay, the total force is the pressure at the centroid times area. Okay, but if I don't show you why that is the case, then it's really easy for you to get confused. Okay. Yes, we will see this in the recitation. This is very important. This is key to fluid statics. So we will see an example of this. But then again, let me stress this. You don't need to memorize this formula. You don't need to memorize this, as long as you understand that the total force is just the integral of each individual small forces. If you keep that in mind, then you will be able to solve any problem. Okay. But nonetheless, it could be handy, you know, so you don't have to do the full integral. If you have a wall, you know that you just need to know the pressure at half point, at half depth, times the area of the wall, and that's the total force. You don't need to use your brain much. But what happens, for instance, in this case? Okay, let's say you have a wedge, like I was asked recently. Let's say you have a funny pool, which has this shape. Okay, and we're gonna call this H. Oh, I'm sorry. We're going to call this H. And for the sake of the argument, this is going to be H2. Okay. So what's the total force applied on this wall?
I think I got the thing that the pressure in the left side is going to be the same at the right side.
Yeah, you're right. So let's say we don't know anything about the right side. So you only see a straight wall. So the pressure we already showed. The total force, we're going to call this 1 and this 2. Okay. So the force at 1 is going to be the pressure at the center of gravity times the area, which is going to be gamma h half times the area. It's h again, and again we're always considering 1 meter depth, but keep in mind that we could tell you, you know, this is 5 meter depth, or a depth, or I mean, yeah, a bottom, you know, how you say, yeah, in the y direction of whatever magnitude. So again, it's gamma h square half, easy peasy. Let's say we try to compute this other guy, FR, okay. Okay, well, FR, I mean F2. Please realize two things: that there's gonna be on every surface, the force acts in a normal direction. Okay. So that's important. So F2 is the normal to the surface. F2 is going to be, again, we're going to call this 1 and 1 so we don't mess up. It's going to be P, the pressure at the center of gravity of 2, times the area of 2. Okay. The pressure at the center of gravity of 2, here 2 is all of this, right? So the pressure at the middle point, again, is gamma h half, but the area now is different, right? So if this is h and this is h, this should be square 2 of h. Yes, right? So the area is going to be h times square 2. So this is basically, it's pretty much the same as before, but we have that square 2 on front. And why is that? Because as you well put, if you have F2, well, this is gonna be F2 set, let's say, set, stupid stylus, and this is gonna be F2 x, yes, and this is theta, and theta is cosine 45. So F2x is gonna be F2 cosine theta, and F2 set is going to be the same, F2 sine theta, but since theta is 45 in this case, right? So these two are the same, and I think it's 1 over square 2. If anyone can confirm, that would be great. So this should be 1 over square 2, 1 over square 2. So you're right. F1 has to be equal to F2 projected on X. Has to be. And you can check it on your own. F2 set should be equal to the weight of the water, right? So it should be equal to this volume times gamma. I'm going to leave you to prove that. But it has to be, because otherwise it wouldn't be on equilibrium. Okay, I hope that's clear. Moving on to the final point, which might be a bit dense. So yeah, we have a question. The triangle of pressure should also produce an axial force. What do you mean by an axial force? In the pool, you mean? In the material of the pool? Yeah, look, this is very important because it depends on the level that you want to go. I mean, if you're a structural engineer, I'm sorry, because F2 would be perpendicular force. Yes, F2, actually what you have, probably you saw on a statics. Let me just draw this. Let's say you have a structure like that, and you might have a point force, and you might have a distributed force, right? And what you normally do in a this should be Q and this should be X. And this is I don't know, a rotating stuff. I didn't enjoy much statics. But normally what you do here is that you compute the shear and the momentum, and right, you compute all of those. So in your pool you have the same. Normally we can say one resultant force, but you have to realize and you have to keep in mind that you have a distribution of forces, and therefore a part of your wall is compressing and another part of your wall is what's the opposite of compressing? Is under traction, right? And they're going to be internal moments. We're not going to compute those here in this course, but you need to be aware that those exist, and that if you're a structural designer, you need to take them into account. Okay, I don't know if that was your question or I just drifted away. But yeah, the thing with equivalent forces is that they're easier to digest. But in reality, under a fluid, you're always going to have a distribution of forces because you have a distribution of pressures. Okay. But what we're interested here is that you're able to compute the resultant force. Let me just draw, delete this because it's not relevant for us. Okay, I think I won't have much time for this, so I will just go over it very, very quickly, and we'll see it again in next class. Okay, we know the pressure on the wall of the pool, and we can compute it regardless if that wall is inclined or vertical. Okay, that's more or less easy. So the total magnitude of the force we know. But the other interesting question is, where is this force being applied? Okay. And again, I can give you the equation, but my worry is that you take the equation by heart and you don't know what you're doing. Okay, so the idea is this. Let's say we know the force, the resultant force. We want to know the application point. We're going to call this YR. And that application point has to be such that the sum of all little forces, dF, times their particular arm are equal to the main force. This is, if you're not familiar, this is equivalent to the sum of torque around. In this case, it's not, I'm sorry. Yeah, we're going to keep this. This is the sum of torque or moment should be 0. So this part here is the sum of torques, and we're saying, okay, this sum of torques has to be the same as the total force times a certain arm or a certain distance. This is what we want to compute, because this is, okay, straightforward to compute, but this one can be trickier. Okay, so bear with me this couple of minutes. So what you normally do is that we know already dF, right? So let me just write this down a bit differently. So let me put y first, and we know that dF is dP times area, and dP we know is y gamma times y times sin of theta times dA. Okay. And again, we can get gamma and sine of theta, and we get I squared dA over area. This guy here, if you remember statics or maybe solid mechanics, this guy here is called the moment of inertia. This is called moment of inertia, and is a measure of the resistance to moving around, to rotate under a certain axis. So this is going to be y x, because x is the axis perpendicular to this y that we're defining. Don't worry if this is confusing, because it is, but we'll see it in the next class in more detail. No, is the x well? Look, we were defining this as follows, right? We were saying, okay, this is the surface, and this is y, right? And we were defining x. In this case, you can consider x to be getting into the screen. So x is going. We normally draw this like this, right? Oh, crap. Like this, right? So x is going into the screen. So this is, if you hold your pencil over the screen, Ix is the moment of inertia around that axis. Okay. Now, I find this confusing, and I find this not very handy. You can show later on that the position of the application of the force is related to the centroid of your surface. Okay, I won't do that now because I want to do it with time. But it's basically it's a function that depends on the position of the centroid. It's going to be always below your centroid. So let me give you spoiler. Again, if we continue with the pool, and we say this is H, the application of the force is going to be below. It's going to be below the center of the center of gravity. Okay. Actually, should be 2/3 of H. Okay. But we're going to see it later on. So you can remember this equation, or you can actually compute the integral. Okay, which for simple areas, at least for me, it's easier because I don't know the moment of inertia of every surface. Of course, in the exams or in the midterms, we're going to give you the moment of inertia, but the risk that you run is that you just use it this blindly without really understanding what you're doing. Okay, so I won't rush into this. I want to do it calmly. So we'll start next class with this computing the application of the resultant force. Okay, so that's for today. Before we go, remember we're gonna have the quiz starting this Friday up until Monday after class. So I recommend you read the book. Chapter 2 should be this class, and next class. Chapter 2 covers both of them. So that's my recommendation. And okay, it's pretty late, so thank you very much for being here. See you guys next Monday. All right? Cheers.